students and engineers on the NYU CubeSat team. The CubeSat needs some kind of computer in order to manage all the onboard functions and control all of its peripherals and payloads. In order to do that, it has what's called a flight computer. This is somewhat similar to an average home computer, however, it's less powerful and it's specialized to what the CubeSat needs to do. It also has to withstand radiation and be tolerant of high and low temperatures. To that end, we're using a flight computer on this red circuit board over here, which is rated for a certain level of radiation tolerance and also includes an inertial measurement unit in order to sense the orientation of the CubeSat. The flight computer also communicates with the laptop using two different communication mechanisms. The second communication mechanism over here is called a CAN bus and also communicates with other modules further downstream on the CubeSat. Here you can see the data the flight computer is printing, and it's basically printing the orientation information.
Hi, my name is Easton Smith. I am developing the mission science payload on Nyusat. The mission science payload is the two middle modules on the satellite. It consists of GPS, pressure, relative humidity, temperature, and a Geiger counter as well. It also has navigation. It takes navigational readings as well. It sends them to the OBC. This is a lot of data. In order to process all of that data, we have a STM32F4 ARM Cortex, which is running a real-time operating system, a deterministic operating system, in order to process that data concurrently. We're processing it in 7 different threads currently, and all of that data is sent out of the CAN transceiver out to the OBC.
Hi, my name is Danny, and I'm in charge of powering the CubeSat. For that, we're using solar panels, and we're using 4 in series 1860-50 lithium-ion cells. As we know, the amount of voltage seen for the panels depends on the amount of sunlight received by each panel. To charge the battery, we need a constant current, and for that comes the MPPT, maximum power tracking. It consists of delivering, no matter the amount of voltage seen by the solar panels, we deliver a constant current to charge each battery.
Hello, I'm Pedro.
And I'm Matt.
And we are in charge of the communication subsystem for the CubeSat. Our satellite is using turnstile antenna, which is essentially 4 monopoles. It allows circular polarization, which means that our CubeSat will be able to communicate to ground station in any orientation. The antennas are essentially made from tape measure material, which allows them to be flexible, which we need because we need them to be stopped while the CubeSat is being deployed. The antennas being fed from the antenna feed PCB, which essentially has all the circuitry for circular polarization. And that PCB is being fed by the transmitter that will be sitting below on the stack.
The transmitter transmits at 144 megahertz, which allows us to use the APRS system. This means that we can receive signals without a big reception system of our own on the ground. It also interfaces with the STM32 microcontroller, which communicates to the rest of the boards in our stack using CAN bus. This means that any of the boards can be taken in and replaced with something else, or reconfigured into a different orientation if we need to do that for a certain project. I also designed the frame for this system, which is mainly to be easily 3D printable so that it can be made anywhere.
In the 1990s, the CubeSat program reduced the monetary barrier to orbit. With our new system, we hope to reduce the intellectual barrier as well by providing an easily modified modular system for CubeSats.